It's so crazy that I was able to like pull in
Ah, yes. Oh, yeah. Sorry, I just realized I read that in your email, but I forgot to answer it. So for finite differences, you're not going to use a third order scheme. So you're going to use the fourth order scheme that we talked about before. So third order is for finite volumes, and that's the quick scheme that we're going to do today. But for finite differences, you're going to use the fourth order scheme that we did last time. Yeah. Mhm. Yeah, save that one for last. And so make sure you implement the code with just kind of the basic schemes first, all the second order schemes, and then once that's working, then you can upgrade it to the higher order scheme. Because for this, for last year's project, it made a big difference in between the results, but for this year's project, it actually doesn't make that big a difference. And so if you can implement it with the basic schemes first, that's already most of the battle there. Then you'll have a good reference then. Then once you implement the higher order schemes, it should look basically the same as your lower order scheme. Yeah. Mhm. Portable X-ray machine, is that even legal? I don't know if yeah, that's what I imagine, because it's a lot of radiation. I don't know if you want to put that in the hands of general civilians. A little radiation, but not. But I guess I guess I'm imagining like someone's 6-year-old kid like taking the X-ray and then kind of shining it at everyone in the room. So a little radiation doesn't hurt, but a lot of radiation can mess you up. Yeah, it would be something if if someone invented something or made it safe enough for home use. But yeah, the way the technology works right now, I don't see it. That's probably true, but that's in the hands of a skilled technician, though. That's the I think that's the key thing. Yeah, I think most radiation machine, or most X-ray machines, in the hands of a skilled technician, won't do anything to you. But it's when you give it to just randos on the internet, that's when things get a little bit dangerous. Yeah, that's true too. Okay, it's 5:30, so let's go ahead and get started. All right, so good afternoon, everyone. How's everyone doing today? Swamped. Yeah, it's busy time. It's it's that time of the semester, but we're almost there. And so after today, then we'll have just 2 more weeks of the semester left to go. So we're almost at the end, guys. So just hang in there just a little bit longer. Okay, so and so speaking of that, so today the plan is we're going to finish our lecture notes on higher order schemes. And so I think we left off right in the middle of the quick scheme. And so we'll finish that up. And then after that, we'll start going over the last set of lecture notes that I have for this class, which is unsteady problems for finite volumes. Okay. All right, so we are ending, quite a bit early, and so if things go according to schedule, I think we should finish up all of the kind of the core content for this class at the absolute latest by the end of next week. And so kind of like what I promised you at the beginning of class, that what my plan for the last week of class is, I'm going to look up how to run OpenFOAM simulations, and then we're going to do some tutorials on that. And so if you're not familiar with OpenFOAM, OpenFOAM is one of the bigger open source software projects out there that lets you simulate fluids and heat transfer, like on a much bigger scale, right? And so OpenFOAM is basically, I actually don't know how OpenFOAM was formed, but you can imagine, it probably formed, maybe someone took a class that's similar to this, and they decided to take, their class project and just turn it into a huge open source project. Right? I don't know if that's actually what happened, but it could. Because one of my good colleagues, like he took not a class like this, but he took a finite element class, and he wrote kind of the beginnings of a larger code base for his final project, and he turned that into a huge finite element solver that's used by a lot. It's not as famous as OpenFOAM, but it's one that I've used quite a bit, and it's nice. So and so I think that'll be nice, because with OpenFOAM, you'll be able to tackle much more complex, much more realistic engineering scenarios, whereas kind of everything that we've been doing up to this point in the class has kind of been more a little bit more basic problems, just because we're focusing on the theory. But now that you have the theory down by this point, then I think you guys are ready to use kind of a much bigger code so that you can actually apply it to real problems, right? And so OpenFOAM is one of those softwares that maybe doesn't get as much name recognition as SolidWorks or ANSYS, but it's definitely respected by industry. And so we'll be learning it for a week, and we'll just be doing the basics. But if you continue on with that and learn more, that's a marketable skill that you can put on your resume. And so yeah, hopefully you guys are looking forward to that. All right, so the other announcement I have to make is that the midterms, I haven't started grading them yet. So I'm in the middle of grading midterms for another class, and so I'm planning to finish that up later this evening. And then the midterms for 417, I'm going to start grading tomorrow. And so by the end of the day tomorrow, you should have your midterm scores. Right? And so I'll send an email when I'm done grading them, and then at that point you'll know what you got. Okay. And so I don't really have anything else to comment on that, because I literally have not even taken a look at them yet. But I'll send an email tomorrow, and then we can talk about it more on Monday. Okay. Oh yeah, one more thing. So I do have one more homework for you guys that's planned, mostly based around the higher order convection schemes and the unsteady FVM. And so kind of the last 2 topics of the class. But since we're not finished with higher order schemes yet, I was planning on assigning that either end of this week or on Monday, and then that'll be due on the very, very last day of class. Not the Wednesday, but on the Friday. And so it'll be Friday of week 16. And so 16 days from now, okay? And so after I sign it, you'll have about 2 weeks to complete that last homework assignment, okay? And so in terms of, assignments that are graded for this class, there's only 2 that are left. And so there's homework 7, which is or I guess homework 6, sorry. Homework 6, which is what I'm going to assign next week. And then the final project, of course, which I think, I think a lot of you guys are starting to work on now, because I've answered a few questions on that the last couple of days. Okay, so that's the plan going forward. And so are there any questions before we get started for today? Okay, all right, so let's go ahead and pick up where we left off. Okay. And where we left off was on higher order schemes for finite volumes. Right. And so the whole theme of this set of lecture notes, this lecture notes 12 right here, has to do with the fact that we're using a better scheme to discretize the convection terms, right? Okay. Because the convection term has all kinds of issues with it, things like instability, things like cross-stream diffusion, and so there's a lot of issues with the convection term. And so the logic here is that if we use a better scheme for it, then a lot of these problems will go away. Right now we're still working on notes 12, and so we're on the last bit of notes 12, and then after that we'll move on to notes 13. Okay. And so the scheme that we're looking at for the finite volume method was a method called the quick scheme. Right? And so I'm not going to write it down again because what the acronym stands for is not that important. But quick scheme stands for quadratic upwind interpolation for convective kinematics. Okay. And the idea with the quick scheme is to incorporate more neighbors into our estimation of the face value. Because normally we when we're estimating our face values, we usually only incorporate two of our neighbor terms, right? And so just as an example, let me draw two finite volume cells here. Okay. So let's say that we have these two cells, and we'll call this phi sub c. We'll call this phi sub e. Okay. Remember, as part of the finite volume scheme, specifically for the convective terms, we're responsible for estimating the values of phi right in between the cells. Okay. Right. And so what we've done in the past, and kind of our lower order scheme, is we just simply took the average of the two most neighboring cells. Okay. And so we said phi sub little e is equal to phi sub c plus phi sub big E divided by 2. Okay. And so that's what we did for a lower order scheme. Okay. And kind of the motivation behind this was we just drew a straight line in between phi sub e and phi sub c, and then we just took kind of the midpoint or the mid value between them. Okay. All right. And so the idea with quick is that instead of doing a linear line here, we're going to use a quadratic one. Okay. And a quadratic term or quadratic equation is going to require 3 points instead of 2. And so kind of what we talked about last time is there's kind of two different versions of the quick scheme. And so you can have one that's shifted. We do include one more neighbor to the left, or we can do a quick scheme where we include one more neighbor to the right. Okay. And which one that we choose, remember, depends on the direction of the velocity. Okay. And so on the next page, I'll go ahead and summarize the two versions for you, and then we'll jump back into the example that we started last time. Okay. All right. So any questions on this so far? This is just a recap of last time. Okay. And so let's go ahead and recap the two different versions of quick. Okay. All right, so version 1. So version 1 looked like the following. And so for version 1, we're going to incorporate an additional neighbor on the same side as the face. Okay. Wait. Oh wow, I screwed that up. I put the on the previous page. I put phi sub e on the left when it should be on the right. So like, wait a minute, this is weird. Okay, so I'm gonna do it right this time. Okay. Okay. And so in version 1, we're going to include another neighbor on the same side of the face. Because we're just like before, we're looking to approximate this value right here. Okay, phi sub little e. And so when I say we put an additional neighbor on the same side of the face, right? Because originally we're trying to form the equations for this cell right here, phi sub c, right? And so this face right here, phi sub little e, is on the kind of the right or the east face of the cell, okay? And so if we include another neighbor in that same direction, then we're going to have phi sub 2e, okay? All right. And so in this version of Quick, then phi sub little e is going to be 3/8 phi sub c, okay, plus 3/4 phi sub e, okay, minus 1/8 phi sub 2e. Okay. And then since we have, since this scheme is kind of lopsided to the right, this works best when the velocity is coming from the right. And so in other words, if the velocity is going from right to left, which is negative. Okay. All right, and so that's version 1. And so version 2, we're going to put our new neighbor on the opposite side of the face. Okay. So let me give myself a little bit more room here. Okay. We're once again, we're focusing on this phi sub c here. Okay, so we're focusing on this cell. That's the one we're forming the equations for. And the face value that we want to approximate is this one right here. Okay. And so in version 2, the equation looks like this. So we have minus 1/8 phi w plus 3/4 phi sub c plus 3/8 phi sub big E. Okay. Right. And since this puts an additional note on the left, this works well when the velocity goes from left to right. Okay. In other words, when the velocity is greater than 0. Okay. All right. And so those are the two versions of our quick scheme that we're going to use. Okay. And so your goal when you're writing your code or when you're developing these equations for quick is to first determine which way the velocity is coming from, and then depending on which way the velocity is coming from, that's going to determine which of these two versions that you're going to use. Okay? And so in the next example, I'm going to show you how to do this for all the different face integrals. Okay, because right now we've done this example for just on the east face, but in reality when you do finite volumes, you have to do it for the east, the north, the south, and the west face, all 4 of them. Okay, so any questions on this before we jump back into the example? Okay. All right, so the example looks like this. Okay, so the example is, let's say that we have 10 partial phi partial x plus 75 partial phi partial y is equal to 3 partial squared phi partial x squared plus partial squared phi partial y squared. Okay. And then from this equation here, we can see that u is equal to 10, and v is equal to 75, and k is equal to 3. Okay. And then let's see, I think we'll assume that delta is given. Okay. But I'm gonna leave the solutions in front of delta. Okay. All right. And so in this case, both of our velocity components here are greater than 0. Okay. And so this tells us that the velocities are going in the positive direction. Okay. And so for the u velocity, this tells us that the x velocity here is going from left to right. Okay. In other words, it looks like that. Okay. And then for the vertical velocity, the y velocity here, that's going to go from down to up. Okay. In other words, it looks like that. Okay. And so we're going to use these velocity directions to help us with choosing which quick scheme that we want to use. Okay. All right. And so let's start with just the east face, because we've kind of done that before. Okay. And so what we're going to do now is we're going to evaluate all finite volume face integrals. Okay. All right, so let's start with the east face. And so the east face, we have two versions here. Okay. Okay. So version 1, we have u times minus 1/8 phi w. Actually, let me keep it consistent with what we had before. So we have minus 1/8 phi 2e. Okay. Plus 3/4 phi e plus 3/8 phi sub c. Okay. And then, it's not used here, but let me include the diffusion term because we can't forget that. Okay, so we have minus k phi sub e minus phi sub c, all divided by delta. Okay, and so that's the first version. And then for the second version, we're going to use the other quick scheme. So the other quick scheme is u minus 1/8 phi w plus 3/4 phi sub c plus 3/8 phi sub e. Okay. This is minus k phi sub e minus phi sub c all divided by delta. Okay. And remember, with the diffusion term, we just leave that alone because the diffusion term is perfect and we love it, and it has done absolutely nothing wrong. Okay. All right. And so based on which direction the velocity is going, which of these quick schemes should we use for this problem? Right. So we know the velocity is coming from left to right, right? And so we want to choose a quick scheme that places more emphasis on the left side of the cell as opposed to the right, right? And so let me draw the cell here just so you can kind of see. And so for the east face integral, we're evaluating this phi value right here, okay? And so since the velocity is coming from left to right, we want to pick the quick scheme that places more emphasis on that way. And so for this case, it's going to be this one, okay? And so for this one, you can see that we have phi w incorporated into the equation. And so that's going to place more emphasis on the left, whereas the other version of the quick scheme, we have phi 2e. And so that places more emphasis on the right side of the cell, which is what we don't want. And so in this case, we want to place more emphasis on the left because that's where the velocity is. That's where the velocity is coming from. Okay. All right, any questions on this and why we chose that one for this scheme? Okay. All right, so that's one integral down, and so let's go ahead and choose the and do the next one. Okay, and so that one was easy because we've kind of seen that one in the previous examples, right? Oh, question. So what's the first phi term for the top equation? Oh, that's phi 2e. Yeah, and so that's our neighbor two away. Yeah. Mm-hmm. All right, and so now let's do the next integral on the list, and so now let's do the south integral. Okay, and just like the east integral here, we're going to have two different options. Okay, and so let me write version 1 first. Okay, and so version 1, we're going to put an additional neighbor on the same side of our face. Okay, and so for the south integral, that's going to be minus 1/8 v2s. Okay, plus 3/4 phi s. Okay, plus 3/8 phi c. Okay, and then we have to include our diffusion term, and so our diffusion term is a plus k phi sub c minus phi sub s divided by delta. Okay. All right, so that's the first version, and the second version is going to be a minus v minus 1/8. This time we're going to go the other direction, and so instead of adding a neighbor to the south, we're going to add a neighbor to the north. Okay, so we have a minus 1/8 phi north plus 3/4 phi sub c plus 3/8 phi sub s. Okay, plus k phi sub c minus phi sub s, all divided by delta. Okay. All right. And so based on the direction of the vertical velocity, which of these schemes should we use? Okay. So we know the vertical velocity is going from down to up, right? And so we want to pick a quick scheme here that that places more emphasis on the south more than the north. Right? And so in this case, we want to pick the first version here. Because this first version places our new neighbor to south of us, right? And so that's why we have phi 2s, right? And so this is the one that we want to choose because our velocity is positive here, okay? Positive v. All right, and so that's the south integral. And so now let's pick the west one. Okay. All right, so for the west one, we're going to have two options here as well. Okay. And so let me do version 1 first. Okay, so we have a minus u times minus 1/8 phi 2w, okay, plus 3/4 phi w plus 3/8 phi sub c plus k phi sub c minus phi sub w, all divided by delta. Okay, and so that's version 1. And then version 2, we're going to go the other way. So version 2, we're going to have a minus 1/8 phi sub e plus 3/4 phi sub c plus 3/8 phi sub w. Okay, plus k phi sub c minus phi sub w, all divided by delta. All right. And so, once again, we have to choose which one of these that we want to use, okay? And since our velocity, our x velocity here, our u, is going from left to right, we want to pick the one that places more emphasis on the left. And so that's going to be version 1. Right? And so version 1, you can see that we have our neighbor 2 west of us, or phi2w, okay? And so that's going to place more emphasis on that compared to the right, okay? Okay. And so that's the west one, and we've done the south and the east, and we have just one more, which is the north integral. All right. And so our north integral looks like the following. It's a lot, I know. Yeah, it gets overwhelming, and so finite volumes is already kind of a lot to evaluate, and then once you throw this quick scheme where you have to choose, in between the two, it becomes quite a lot. But this is the last one, I swear. Okay. All right. And so let me do version 1. And so version 1, we're going to put another neighbor on the same side, which is on the north. I told you it wasn't quick. Quick is just the name. It's not actually quick. Right, and so we have a minus 1/8 phi2n plus 3/4 phi n plus 3/8 phi c, okay, plus, minus, because it's a north integral, minus k phi sub n minus phi sub c, all divided by delta, okay? Then version 2, we have a v, we have a minus 1/8 phi sub south, right? Plus 3/4 phi sub c plus 3/8 phi sub n, okay? Minus k phi north minus phi c all divided by delta, right? All right, one last time. And so, remember, we want to choose the phi direction, or we want to choose the quick scheme here that's going to place us, that's going to place our more emphasis on where the velocity is coming from, okay? And so since the velocity is coming from the south here, right, because our v here is a positive 75, then for this case, we want to choose version 2 because that's going to place one neighbor to the south as opposed to the north. And so for the east one, we chose version 2 because version 2, our velocity is going from left to right, and so we want to place more emphasis on the west one. Yeah. I told you, quick was just an acronym. It's not an acronym. It has nothing to do with how fast it is. All right. And so this is kind of the decision-making process that you would have to do for this, right? And so depending on the direction of the velocity, you would choose one scheme over the other one. Okay. All right. And so this is the case when your velocity is always going in the same direction, right? And so I'll tell you what the grad students of last year had to deal with, and they were dealing with a situation where, what if your velocity is changing directions as you go about the simulation, right? So let's say that you have an unsteady simulation and your velocity is changing. Sometimes it's going to the right, sometimes it's going to the left, sometimes to the right and the left. And so what they had to do was they had to incorporate this into their projects, where they had to write an if statement that said, if the velocity is going this way, and do this scheme, but if the velocity is going the other way, do the other scheme. And so for this year's project, you don't have to do that, because this year's project, the velocity is only going in one direction. But, that's just kind of just to give you an idea of what they had to deal with for last year's finite volume project. Okay, so any questions on this before we jump into the MATLAB implementation? Okay, so let me go ahead and look and see how this is implemented in MATLAB. Okay, so let me go ahead and share my screen. Right. And so actually this MATLAB code that I have here does incorporate that. And so you'll see, a bunch of if statements here, that show you, how you would implement one way or the other one. Okay. All right, and so this is a code that's on Canvas. And so this is the 2D convection diffusion FEM higher order. Okay. And so actually, let me show you where it's uploaded. Okay. And so you go to week 14 here. Okay. and then you go to this one right here. And so this is the code called higher order FVM example. Okay. All right, so let's see how this is implemented in practice. All right, and so this is a steady problem, and so we don't have any time loop here, but we do have loops for I and j. Okay. All right, and so just like we saw for the higher order finite difference scheme, you see here that we have to compute some more neighbors. Okay, and so this section of code right here computes the ID numbers for all the distant neighbors. Okay, and so we have west ID 2, and so that's going to compute the ID number for phi to 2w. Okay, right, and so east ID 2, this is for phi to east. Okay. Next, we have north ID 2, so this is phi to n, okay? And then south ID 2, this is phi to s, okay? Right? And so that's the first major addition here is the, we have to compute these IDs. Because besides that, everything else here is the same. So in section 1 here, we define all of our variables. And so we define the length of the domain, the number of cells in each direction, the left-hand side matrix, all the parameters and all that stuff, okay? We enter into the double for loop. And just remember the double for loop, this is needed because we're going to visit every single cell in the grid, okay? And then we compute the ID numbers for all of the, for my ID, which is phi sub c and all of its immediate neighbors. And then since we're doing the quick scheme, we have to do the all the distant neighbors as well, all right? Okay, and so that's the first new addition here. And so let's jump into each of the different integrals, okay? And so you can see I've split this up in the same way that we talked about, I think, kind of right before the midterm. And so I split this code up into each of the different integrals, okay? And so you can see, the way I've implemented this example here is for kind of the most general case, okay? And so, this code here is a little bit overkill for this particular example because, we know the velocity is going in one direction. But if the velocity is going in a different direction, I have the code here that kind of shows you how to do it too. Okay, and so this was mainly for the project last year, where I did make them implement cases where you have to go either one direction or the other one. Okay, all right, and so you can see here there's a ton of if statements, and so it's like exhibit, right? And so we have if statements in our if statements because we love our if statements. It wasn't as bad because I did kind of the same thing for them as I did for you guys, where I'd fully implemented one of the integrals for them, and then all they had to do was kind of just apply the same concepts for the other integrals. Yeah. All right. Okay, and so let's look at this east integral and see how everything is implemented. Okay, and so you can see here there's actually 5 different cases that we have to worry about. Okay, and so we'll go over each of the 5 different cases kind of slowly. And so the first thing that we have to worry about here is if I is equal to nx, okay? And so if I is equal to nx, what this tells us is that we need to apply a boundary condition on our integral, okay? And so we can't forget about that, okay? And so in this case, we have a Dirichlet boundary condition, which is phi is equal to 25, okay? And so this incorporates the coefficients both in the left-hand side matrix as well as in the right-hand side vector for the boundary conditions. And so this is nothing new. And so this is kind of exactly the same as what we've done before when we did 2D convection diffusion with finite volumes, okay? And so, whenever you're performing these integrals, first thing you should always check to see is if you're on a boundary. And if you are on a boundary, then you have to apply the boundary conditions, okay? All right, and so from here, if we're not on a boundary, then the next thing we check is we check the direction of the velocity, okay? And so it's a bit hard to read here because there's a lot of if statements, but this if, this else if, and this else statement right here, because they're all indented the same, all of these guys go together, okay? And so the way to kind of read this is that, first the program is going to check to see if I is equal to nx, okay? And so it's going to check to see if we're on a boundary. If we're not on a boundary, then the next thing it checks is the direction of the velocity, okay? And so the next thing it checks to see is else if u is greater than 0, okay? And so if u is greater than 0, this is the case that we actually do have in this example, then our velocity goes from west to east, or in other words, it goes from left to right, okay? All right, and so if this is the case, then what we can do is we can apply, what was it, version 2, yes. Okay. apply version 2 of Quick here, okay? And so we're going to pick the version where we add our additional neighbor on the other side of the face, okay? And so in this case, it's going to be phi w. Our three phi amigos here are going to be phi w, phi c, and phi e, okay? And you can see here that I've added the quick coefficients here, okay? And so for phi w, you can see I have a -1/8 times u times dy, okay? For phi sub c, I have a 3/4 times u times dy. And then for phi east, I have a 3/8 times u times dy minus k, okay? Oh, for phi sub c, I have a plus k here too, okay? So we can never forget our diffusion term, because remember, we love our diffusion term. It's done nothing wrong, and we don't have to change it at all, okay? Okay. And so that's that's a pretty straightforward application of our hand calculations. Okay. And so what the heck is this thing, right? And so we've already determined that u is greater than 0, but why do I have two different cases here? Okay. And so this first case is when we have, if you read the comment here, so this is when we have enough neighbors for quick, right? And so if you remember when we did the higher order scheme for finite differences, one new thing that we have to check here is we have to check to make sure that we actually have enough neighbors to pull off our scheme, okay? Because that's not always a given, because if we don't have enough neighbors, then the code is just going to not be happy. It's going to give you an error, okay? And so in the case where our u is greater than 0, but we don't have enough neighbors for quick, or in other words, we don't have a west neighbor here, right? Then what we do is we go back to our basic central scheme. Okay, and so our basic central scheme for phi sub little e is going to be half phi sub c and half phi sub e. Okay, and that's what you see right here and right here. Okay. All right, and so there's two things you need to check. And so first thing you need to check is the direction of the velocity, and that's going to determine which version you're going to use. But before you do that, you need to check to see if you actually have enough neighbors. Okay. And so you can see the check that I use here is I check to see if I is greater than 1, okay? And so if I is 2 or 3 or 4, then we know that we have a west neighbor, because we know we have something on that side, okay? And that's going to give us that phi sub w that we need, okay? All right, and so that covers this block of code right here for what happens when our u is greater than 0. Okay. All right, so any questions on this so far? Okay. All right, and so now let's go to the other case, right? And so now that we've exited this else if u is greater than 0, now we're dealing with the case where our velocity is negative, right? And so in other words, the velocity goes from east to west, okay? And so if that's the case, and if we have enough neighbors, then we're going to apply version 1 of quick, okay? And so in version 1, we're going to put another neighbor on the same side of the face. And so now we're going to have a phi 2e, in addition to phi sub c and phi sub e, okay? All right. And if you look at the coefficients here, they're the same as what's in the note. So we have a 3/8 on phi sub c, we have a 3/4 on phi sub e, and we have a -1/8 on phi sub 2e, okay? And then same thing is, if we don't have enough neighbors, let's say that we don't have a 2 east neighbor, right? And so if east 2 ID doesn't exist, then what we have to do is we have to go back to our basic central scheme, okay? And that's what we have here. And so for this particular code, or for this particular example, this code that I've highlighted here actually never sees the light of day, right? Because remember, our u, our velocity here is fixed at a +10, okay? And so there's no chance, for this velocity to actually go negative, okay? And so all of this code right here is actually, kind of actually useless in this case, because, our velocity is just never going to go negative, okay? But I included it here just to kind of show you how to write this program more generally, so that you can account for these things. Because let's say that we're doing an unsteady problem, and our u was, instead of 10, it's 10 times sine of t, okay? And so in that case, our u velocity is going to oscillate, so it's going to go forward and back, forward and back. And so our code is going to need to be able to handle both of those situations where velocity is either positive or negative, okay? And it needs to apply the correct quick scheme for that, right? Okay, so any questions on the East integral as a whole? Okay. All right, and so that's the East integral. So it's quite a lot to parse here. So it's it's a lot of if statements, but if you go at it kind of step by step, watch the lecture again and kind of try to see why I did each of these steps, then hopefully it becomes a bit clear. Okay. All right, and so you can see I've of course written down all the other integrals here. Okay, so we have the South integral, we have the West integral, and the North integral. Okay. I'm not going to go over these in detail because they're kind of a repeat of what's set up here. Okay. But just like we did for the East integral, we're gonna check to see if we're on a boundary, okay? And if we're on a boundary, then we apply our Dirichlet boundary condition, okay? But if we're not on a boundary, then which quick scheme that we use depends on the direction of the velocity, okay? And so first we see if the v is greater than 0, and if it is, we're gonna apply this quick scheme, which I believe is version 1, okay? But if the velocity is negative, then we're gonna apply quick scheme version 2, which is what we have down here, okay? And then once again, you have to check to see if you actually have enough neighbors for that quick scheme. And if you don't, then you just go back to our basic scheme. Okay. Right. And so that's the South integral. West integral looks very similar. North integral looks very similar. Okay. So when we go ahead and run this code. Okay. And this is the solution that we get. Okay. All right. And so that's the quick scheme. Okay. And so quick scheme is it's a good scheme to know, especially if you're interested in going into computational fluid dynamics after this, because quick scheme is one of the more popular schemes that they have for that. Okay. All right. And so one really nice thing about quick, if you kind of think back to our regular fourth order central difference, which is what we did for finite difference, compared to that, the quick scheme is only third order accurate. And so in terms of accuracy, it's actually worse than its finite difference counterpart. But the nice thing about quick is that it's stable, right? And so, remember the U in quick stands for upwinding. And so that tells us that no matter what the velocity is doing, we're always going to end up with a stable solution with quick. Okay? And so that's a really, really nice feature. And that's kind of a reason why it's used for so many CFD codes, is because that stability is really, really valuable. And so, if you can have that stability, that's a really nice feature for you to have for your CFD code. Okay. All right. So any final questions on this? Let me just make sure that I got everything here. Yes, it's upwinding. Okay. Okay, so that's higher order terms, and so that's all you need to know about higher order terms. But remember, the challenge that you guys have for the projects is you guys need to combine higher order schemes, which is what we did here, with a time marching scheme. Okay, and so I'm not showing you an example of that on purpose because I want you guys to work that through for your projects yourselves. Okay. And so, to do that part, what you need to do is you need to, obviously apply what we have here in terms of discretizing the equations, but then combine that together with the scheme, with the way that we discretize in terms of time for implicit Euler. And then from there, you're able to get your coefficients and algebraic expression. Okay. And so that's going to be the main challenge for you guys' projects. All right. So let me go back to my, my iPad here. Okay. All right, and so now that we're done with higher order schemes, we're going to go ahead and move on to lecture notes 13, the last lecture notes for this class, and that's going to be time marching schemes with finite volumes. Right. And so this is kind of the last member of the family for our finite volume schemes, right? Because remember, if we think back to our general conservation equation, so the general equation that we're solving, okay, there were four big terms that we had. Okay. Okay. We had our unsteady term, we had our convection terms, okay, we had our diffusion term, And of course, we had our source, okay? So this was unsteady. This was convection. Right. This was diffusion. And of course, this last guy here is source. Right. And so I'm writing this equation again, partially for nostalgic purposes. And so hopefully, this is like, oh man, we've come so far in this class. Look how mature and look how far we've come, right? But also just to kind of highlight that, for our finite volumes, the unsteady term is the last one that we have to do yet, okay? Because for finite volumes, we know how to do convection, we know how to do diffusion, and we know how to do source, okay? And so we can put a nice check mark there, okay? And so the only one that we have left here is unsteady, okay? And luckily for us, the unsteady term in finite volumes is the easiest one to deal with. Okay. And that's because, we don't have to do with any kind of weird integration rules, like we don't have to do divergence theorem, okay? And so we just integrate it. We just kind of just do it just like it is. Right? Okay, and so let me show you that it's the easiest, right? Because normally, when we do our finite volume problems here, you remember the way that we do that is we take our equation and we integrate it over the cell. Okay. And so the unsteady term here is not going to be any different. Okay. And so let me show you what it looks like in 1D. Okay. And so in 1D, we have an integral of partial phi partial t, okay, dx. Okay. Right. And when I say it's the easiest, the reason it's easy is because we don't have any derivatives with respect to space here, right? And so we have a derivative, but it's with respect to time, okay? But we're not integrating over time here. We're integrating over space. That's why we have dx as the integration variable here, okay? And so the evaluation of this is simply just going to be, okay, the integrand here, which is partial phi partial t, and of course we're evaluating this at the centroid of the cell, and then we just multiply it by the size of the cell, okay? And so this is just straight up trapezoidal rule, okay? So this is d partial phi partial t evaluated at centroid. Okay. Where this right here, this delta x, this is just the size of the cell. Okay. And we're dealing with just a 1D case for now, and so our cell is just has a length, okay? But I'll show you the 2D version on the next page, and you'll see that it's just we're just multiplying by the area of the cell. Okay. So any questions on this so far? Okay. All right. So now let's look and see how we do this in 2D. Okay. You'll see it's very similar. Okay. And so in 2D, we have a double integral of partial phi partial t dx dy. Okay. And then just like we saw in 1D, we're going to take our time derivative here. Okay. Evaluate it at the centroid of the cell. Okay. And then we just multiply it by the size of the cell. Where in 2D, the size of the cell is going to be the product of delta x and delta y, because now our cells here are squares as opposed to just a line. Okay. Okay. And so that's it. And so we don't have to we don't have to do much more than that. Okay. All right. But of course, we're not done here yet because we still have this kind of derivative. Okay. And if it's one thing that we hate in this class, it's derivatives, right? Because we always transform these derivatives into algebraic expressions. And so this time it's going to be no different. And in fact, it's going to be exactly the same as what we did before. Okay. Okay. Right. And so partial phi partial t evaluated at the centroid. This is going to be phi sub c minus phi sub c all over delta t. Okay. But for the exponent here, or for the time index, we're going to have n plus 1 minus phi sub c at n. Okay. All right. And so it's literally the exact same thing we've done before, except just that we're except now that we're applying this with finite volumes. Okay. And so all we have to do here is that with this in mind here, all we got to do is we just got to plug this in to all the other finite volume equations that we have for the convection term, the diffusion term, and the source. Okay. Right. And so, of course, once we do merge this together with the convection, diffusion, and the source, we have to put time indexes on, all those different terms. Okay. And what we choose for the time indexes for the convection and diffusion terms, that's going to determine whether we're doing an implicit Euler or an explicit Euler scheme. Okay. All right. So first, I'm going to start out with just 1D unsteady 1D problems with explicit Euler, okay? Because I think those are kind of the simplest ones to do. And then probably next week, what we'll talk about are implicit 2D problems, okay? And that'll actually be pretty similar to what you have on the project. Okay? All right. So any questions on this so far? Okay. And so first, let's go over explicit Euler for finite volume problems. Okay. All right. And so remember, in order to get an explicit scheme, what we have to do is we have to evaluate all phi terms in the convection and diffusion terms right? So we're going to evaluate all these terms at the current time step. Okay. Remember, the current time step is n. Okay. Right. And since all of the solutions at the current time step are known, all of these n terms we're going to move to the right-hand side of the equal sign. Okay. Okay. And so that's kind of just a brief kind of description of what we're going to do. Okay. And so I'm going to show you how to do this with a 1D unsteady problem. And I'm going to keep it simple for now. So I'm just going to involve just diffusion. Okay. Okay. And so the way I'm going to do this problem is I'm going to show you how to derive the equations. Okay. And remember, that's an important skill because you're going to need to do that for the for your projects. Okay. Right. And then once we derive the equations, we're going to write them out by hand, and I'll show you how to implement them in code as well. Okay. All right. And so this example, what we have is partial phi partial t is equal to 3 partial squared phi partial x squared. Okay. Right. And so since this is a 1D problem, we just need 2 boundary conditions. Okay. And so our first boundary condition, we'll have this one vary with time. And so we'll say phi at x is equal to 0. This is equal to cosine of pi t. Okay. And then 2, we're going to have d phi dt at x is equal to 1. Okay. This is going to be cosine of pi t over 2. Okay. And so this is going to be a variation on our wiggling string example that we talked about before. Okay. Okay. And since it's an unsteady problem, remember, we always have to put our initial condition. And so our initial condition in this case is just going to be 0. Okay. So we're just going to work with the simplest one of all. Okay. All right. And so, based on this example here, I'm gonna work on just the equations itself, and I'm gonna derive the time marching scheme by hand, and then if we have time, then I'll show you how this is implemented in MATLAB. Okay. All right. Let me actually write out what we're going to do. So for this problem, we're going to do finite volumes for the spatial discretization. Okay. Explicit Euler for time marching. Okay. And just for the purposes of this hand calculation, we're going to use a mesh with 5 cells. Okay. And then we're going to use a time step size of 0.001. Okay. Right. And so that's the situation that we're going to work with. Okay. Okay. So any questions on this? Okay. And so on the next page, let's start with this equation and let's work through the whole finite volume process. And so I'm going to take this differential equation, I'm going to integrate it, and then we're going to derive, all of the equations for this. Okay. And so remember, this process, I know we've gone through it a lot in this class, but it's important, and it's one of the most important skills I want you to take away from this class is to take, how to take a differential equation and how do we actually discretize it. Okay. All right, and so we have partial phi partial t is equal to k, right? And just like I've done in the past, what I'm going to do is I'm going to split the derivative. Okay? And so instead of having partial squared phi partial x squared, I'm going to do partial x of partial phi partial x. Okay. Right. And just like I said before, since we're doing finite volumes, we're going to integrate this guy. Okay. Okay. And that's going to form our finite volume method. Okay. All right. And so now that we're integrating here, we can just go ahead and apply our integration rules. But since we're in 1D, we don't have to do much. Okay. And so first we're going to evaluate the time derivative term. Okay. And so this is going to be, just like we saw at the beginning of lecture, this is going to be partial phi partial t, evaluated at the centroid. Okay. And then we're going to multiply it by the grid spacing, or the size of the grid. Okay. Okay. Then we have our diffusion term, and since we're integrating with dx, that's going to cancel out that derivative. Okay. It's going to be partial phi partial x, evaluated at the right side of the cell, minus partial phi partial x on the left side of the cell. Okay. Right. And so it's a 1D problem, but you can see that we get two boundary terms, which is what we want for this. Okay. All right. Okay. And so from here we're going to discretize these derivatives. Okay. And so for the time derivative, we're going to use our normal time derivative discretization, okay, that we talked about before. And so instead of partial phi partial t, what we have is phi sub c at n plus 1 n plus 1 minus phi sub c at n, all divided by delta t. Okay. And we can't forget about delta x, because that's still there. Okay. And this is equal to k times, we have partial phi partial x on the right side of our cell. And so this is going to be phi sub r minus phi sub c, all divided by delta x. Okay. Minus partial phi partial x on the left side. And so this is going to be phi sub c minus phi sub l, all divided by delta x. Okay. Right. And before we move on, we have to do something about the right side of this equation, and we have to assign a time index for each of these, right? Because that's what we need to do for our time marching schemes, right? And so for this one, since we're doing explicit Euler, we're going to apply a time index of n on all these guys. Okay, so we're going to do n, 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 n. Okay. All right. And so that's good. And so we are pretty close. Okay. And then from here, all we have to do is we just have to manipulate this equation, or work with it algebraically and solve for phi sub c at n plus 1. Okay. Okay. All right. And so if we do that, let me go ahead and divide both sides by delta x, and then multiply both sides by delta t. Okay. And then I'm going to add phi sub c onto both sides. Okay. And so it's going to be phi sub c at n plus 1. Okay. This is equal to k delta t divided by delta x. Okay. And so that's the coefficient out in front. Okay. In fact, let me pull out an additional delta x, okay, because that's going to be that's a common denominator for everything there. Okay. And on the inside here, what we have is phi sub r at n minus phi sub c at n minus phi sub c at n plus phi sub l at n. Okay. All right. And so from here, all we have to do is just to, oh, I forgot one thing. I forgot this guy. And so we have to add phi sub c at n right here. Okay. And so that gets added over to the right-hand side as well. Right? Okay, and so all we have to do from here is we just have to organize the coefficients. And so we're going to put it in terms of a coefficient for L, coefficient for C, and a coefficient for R. Okay. And then once we do that, then we'll have our time marching scheme. Right. So the last term is not in the brackets, and so this is outside. So actually, let me do this. And here we have phi sub c at n plus this stuff. Yep. Oh, the last term, yes, that's phi sub L. Yep. Mm-hmm. All right. So any questions on this so far? Okay. And so if we go ahead and combine all the like terms, then what we get is phi sub c at n plus 1 is equal to, oh, yeah. Mm-hmm. Right. Yep. All right. And so we combine all the like terms, then what we get is the following. Right? As we get phi sub c at n plus 1 is equal to k delta t divided by delta x squared. And this is the coefficient for phi sub L to the n, okay, plus 1 minus 2k delta t divided by delta x squared times phi sub c at n, okay, plus k delta t divided by delta x squared times phi sub r at n, okay? Right? Right? And so this is an equation that we can just directly apply to all cells that have a left and right neighbor, okay? Okay. And so in particular, for this problem, since we are working with 5 cells, and so this is going to be for cells 2, 3, and 4. Okay. But for the other cells, we have to apply our boundary conditions. Okay. Okay. All right. And so, this part's going to be a little bit new because, we haven't dealt with time varying boundary conditions in finite volumes. And so the process is still going to be the same, but, we have to keep in mind that, this is, that our boundary conditions change with time. Okay. All right. So first I'm going to do cell 1, which has a Dirichlet boundary condition next to it. Okay. Because we know from cell 1 that the boundary condition is cosine of pi t. Okay. And so we need to incorporate this into our equations. Okay. And so I'm going to go through the same process that I did here, where I'm going to start, from a step like this. Okay. And then I'm going to incorporate the Dirichlet boundary condition into that. Okay. All right. So any questions on this so far? Okay. All right, and so for cell 1, since that boundary condition is on the left of the cell, the boundary condition is going to affect our computation of partial phi partial x on the left side. Okay, because normally what we have is partial phi partial x, okay, on the left side. Normally what this is we do phi sub c minus phi sub l divided by delta x, okay? But since we're on cell 1 right here, we don't have a left neighbor here, okay? So instead of a left neighbor, what we have is our Dirichlet boundary condition, okay? And so we're going to change this, and so instead we're going to have phi sub c minus phi naught of t divided by delta x divided by 2, okay? Because remember, when we have our Dirichlet boundary condition, our space or a distance between our cell center and the edge is halved, okay? So that's why we do delta x minus over 2, okay? And so if we plug in, our cosine of pi t from our Dirichlet boundary condition, then what we have here is 2 over delta x times phi sub c minus cosine of pi t. Okay. Right. And so now let's take this and substitute that into our finite volume equation. Okay, and so our FEM expression. Let me start from this step right here. Okay. Okay. And so our FEM expression here. First, I'm going to plug in for the time derivative. Is going to be phi sub c at n plus 1 minus phi sub c at n, all divided by delta t. Okay. Times delta x. Right. This is equal to k. Times phi sub r minus phi sub c, all divided by delta x, okay? And instead of, our expression for partial phi partial x on the left side, let me plug in what we have up here. Okay? So we have minus 2 divided by delta x times phi sub c minus cosine of pi t. All right. And so this now is our finite volume equation for cell 1. Okay. And so just like we did last time, we're going to take this expression and solve it for phi sub c at n plus 1. Okay. And so that's going to involve just a little bit of algebra. And so you multiply both sides by delta t divided by delta x. Okay. And then you're going to end up with the expression that I'll have on the next page. Okay. Okay. So any questions on this so far? All right. And so let's go ahead and write down that expression, and then we'll call it a day for today. Okay. All right. And so for cell 1, which has our Dirichlet boundary condition, we have phi c at n plus 1 is equal to k delta t divided by delta x squared times phi sub r to the n, okay, plus 1 minus 3k delta t divided by delta x squared phi sub c to the n, okay, plus 2k delta t divided by delta x squared cosine of pi t. Okay. And since we're on cell 1, we can just, instead of having just generic c's and r's, we can just fill in the indices directly. Okay. And so instead of phi sub c, we'll have phi 1. The right neighbor for cell 1 is cell 2. And then phi sub c again is cell 1. Okay. All right. And so from here, you can plug in the values for k, for delta t and delta x, then you can get your algebraic expression for this guy. Okay. Okay. So any final questions on this before we wrap up for today? Okay. All right. So that's all we got time for. And so on Monday we'll continue this, and we'll see how we can do this for we'll see how this is implemented in MATLAB, and we'll see how we can do this for 2D implicit problems as well. Okay. All right, and so again, I plan on grading the exams tomorrow, and so by the end of the day tomorrow, you should know what you have, right? Okay, so thank you guys for tuning in today. Hope you guys enjoy the rest of your evening, and I'll see you guys next week.
Thank you.
Thanks, guys.
I had a quick question on
Sure.
something from earlier.
Yeah.
When we were evaluating the phase integrals.
Mm-hmm.
Well, actually, two questions now. I realized I didn't circle the one we chose for the north face.
Mm-hmm.
Which one did we choose?
Oh, this is back for high order schemes?
Yeah, sorry. Yeah, before the time
Okay.
marching stuff.
Got it.
We chose the bottom one. Okay.
Yeah.
I wasn't quite sure why we were picking the ones we were picking.
Yeah, so
I understood what you said, but I couldn't see it in the actual equation, like why we were picking the ones we were picking.
Yeah, that's a good question. Let's take the example of the north face just to see.
Okay.
So I think it's easier. I think if we visualize it, because I think there it's all just equations, right?
Yep. It's all
Okay.
Greek.
Yes. All right, and so for the north integral, let me give myself a little bit more room. Okay. And so here we have kind of a four cells, right? And so call this phi 2 north, call this phi north, phi sub c, and phi south, right? And so the two versions essentially will let us choose which three that we're going to use here, right? Because the thing with quick scheme is that we use only three cells at a time, right?
Mm-hmm.
And so version one, we're going to use this batch of cells, right? And because version 1 has phi sub c, phi n, and phi 2n, right?
Mm-hmm.
And then version 2, let me use a different color. It's different than red. It's green. No, blue. Right. And so version 2, we're going to use these three cells. Right? And so version 2 involves phi sub n, phi sub c, and phi sub s, right? And so we have a choice. So we can either pick, the top three or the bottom three here, right? And which one we choose depends on which direction the velocity is coming from, right?
Mm-hmm.
And so in this particular case, our v for that example was 75, right? Positive 75. And so positive 75, we know the velocity is going from down to up. And so it's going this way like that, right?
Mm-hmm.
And so the idea with the upwinding schemes like this is we want to place more weight on from the direction where the velocity is coming from. And so in this case, since the velocity is going from down to up, the velocity is coming from the south.
So you want to put more emphasis on the down.
Exactly, right.
Okay. So that's why on the west one is going from left to right. So we want to put more emphasis on where it's coming from, which is on the west side.
Exactly, right. So that's why we
And
choose version
the-
1. Yeah.
The first equation we put for the west was the U is which one is it? I remember in the last class I wrote down like U is less than 0 or U is greater than 0.
Mhm.
Is the top term or the top equation always U is less than 0 for
Yes.
how you wrote it? Okay.
Yes, yes.
So we chose the top one because U is less than 0.
Oh, sorry. So for the south and the west one, they're reversed. And so for the south and the west one, we chose the top one because U is greater than 0, because that's going to place more emphasis on the left side, right? That's because we have the phi2w here.
That puts more emphasis on the left.
Yes, because we have phi2.
Oh yeah, because you have 2w. Okay.
Yes.
That's like one more than the west. So,
Exactly.
Okay.
Yes. Yeah. Mhm.
Okay. One other thing. How do we know whether k is positive or negative? So I see for south and west you put positive, and then for north and east you put negative k.
Right. So so that comes, and so I kind of skipped that for these ones because it's just because I wanted to focus on just the quick scheme, but it depends on which direction the normal vector is going. And so
Okay.
for the north and the east, our normal vectors pointing up. Right. Can you still hear me?
No, I can hear you. Yeah. You
Okay,
broke up a little
okay.
bit, but you're good. I heard
Okay. Yeah, I karate chopped my mic and it became unplugged
Nice.
a little bit. And so for north and the east, our normal vectors point in their respective positive directions, because
Okay.
positive x goes to the right and positive y goes up.
Yeah.
And so for north and east, that it just ends up that there's a negative out there for k. But for the south and west, those point in the respective negative x and negative y directions. And so that negative cancels out a negative that's kind of
and becomes a
naturally.
positive.
Exactly.
So like by
right.
default, there's a negative k or there's a minus k.
Exactly. Yes. Yes.
But because negative and positive is negative, negative and negative is positive.
Exactly. Yes.
Okay.
Yep.
Okay. Gotcha. Okay, that makes more sense now.
Mhm.
Got it. Sweet. Okay, I think that was all I had. Thank you
Okay,
for that.
cool.
Thank you for the
Yep.
help.
No problem.
I will see you on Monday.
Yep. See you Monday.
All right. Have a good weekend.
You too. Ronald, do you have any other questions?
Yeah, just a quick question
Sure.
on heat flux in 410.
Yeah. Mm-hmm.
So when you have heat flux at a boundary condition, can you expect to see that like as a function, just a vector, a constant?
No.
I
Yeah.
think most of the examples we had, there was no heat flux.
Yeah. So the heat flux a lot of times it's either going to be 0 or it's going to be just some scalar value.
Oh, okay.
And so the heat flux boundary conditions, you can it's actually good you're taking both these classes, because the heat flux boundary condition is exactly the same as like a Neumann boundary condition that we have here.
Okay.
And so mathematically they're exactly the same thing. It's just we call them just different things for different subjects.
Okay.
And so most of the time it's going to be a certain value, but a lot of times just for simplicity I give it just a heat flux of 0, just because that's kind of easy to evaluate. But for a lot of cases you could have a heat flux. Yeah.
And we could you remember you mentioned 3 cases depending on what location it's at.
Yeah. Mm-hmm.
So like 1, 0, 0, 1, will it correlate to one of those 3 cases, or is that different?
Wait, 1, 0, 0, 1, and what's the third case?
1 second. I believe the first case when it's at sorry, 1 second. Where's my 3 cases? So if the element doesn't border a Neumann boundary condition, you have zeros, obviously.
Yes. Yes.
And then if it's at x equals 1, you have 1, 0.
Yes.
At x equals 2, it's 0, 1.
Yes.
The
Oh,
vector
yes. Uh-huh.
So it'll if there's heat flux or I guess it is a Neumann boundary condition.
Mhm.
So it'll depend on the location. It'll correlate to either 1, 0 or 0, 1.
Yes, correct. Yep. Mhm.
Okay.
Yep. Depending on where it is. Mhm.
Okay. Thank you.
Mhm.
And thanks for all the extra information that you answered at the end. That was really helpful
Oh yeah, of
in
course.
terms of
Yeah.
determining these integrals.
Oh yeah, yeah, of course. Yeah, I know this stuff is it's a lot of math and stuff, and so anything I can do to help it's always good.
Okay. Thank you. Have a good one.
Yep, you too.